message has been recorded.
Welcome to the Understanding Probability of Intercept for Intermittent Signals webcast. We will begin shortly and ask you stay on the line and take this time to log on to the web presentation. The details can be found in your email invitation. Thank you for attending.
I will be your host for today's webcast entitled Understanding Probability of Intercept for Intermittent Signals. We'll begin today's webcast in just a moment, but first let me explain to you a little bit about the system. WebEx Event Center allows you to sit back and have the presentation material advance automatically. To participate in the Q&A session, you can enter questions at any time during this presentation in the question window on the lower right-hand side. The presenter will answer questions at the end of the presentation, but again, please feel free to enter them in at any time. Be sure to address your questions directly to all panelists by clicking on the pull-down menu. We have a lot of people online with us today, so I apologize in advance if we don't get to all of your questions. But if we don't worry. If we run out of time, we will respond to the remaining questions via email. We also ask that you take a moment to fill out the short feedback form that will appear when you close your WebEx session. Now let's move on to the presentation. Joining us today is Ricky Overdorf. Ricky is responsible for product planning of aerospace and defense applications for signal analyzers and signal generators. Within Agilent, he has also served as a business development engineer for electronic system level design solutions focusing on military communications and radar. He has also been an application engineer in Agilent's electromagnetic interference test sector. Prior to joining Agilent, Ricky worked in head-end cable, where he was responsible for maintenance and operation of a satellite link for commercial television. Welcome, Ricky. You now have the floor.
Thank you, Allison. So thanks, everyone, for attending. Today we're going to talk about probability of intercept for intermittent signals. And again, thank you all for attending. Let's get started with this. We have, for those of you who are really good with signal processing and have a lot of background, some of these concepts are going to be pretty straightforward to you. And for the others, I am going to take a pretty basic approach at talking about this. So I think most people, even if you're not real familiar with signal processing, you're going to be able to follow along just fine. Okay, let's get started. So here's kind of what I want to talk about today. Let's look at some use cases and signals and at least get an understanding of what we're talking about. We're going to talk about doing analysis or finding intermittent signals in both the time domain and the frequency domain. We're going to, of course, talk about probability of intercept, being able to analyze a signal that is intermittent. And then the primary use case from a signal analysis point of view is using a real-time spectrum analyzer. We're going to review a basic block diagram of what that is so we can understand how that tool analyzes transient events. We're also going to look at some, as I said earlier, some signal processing basics. What's windowing? How does it affect amplitude and sample rate? As well as how do you display and analyze really, obviously you're a human, things that happen very, very fast, sometimes very, very difficult to understand how that is working. And so we'll talk about display and how we analyze that. And then finally, we'll just finish up and kind of give you a good understanding of kind of what's out there to do those types of measurements. So finding dynamic or transient events, where this is becoming really important, a couple of use cases are, obviously a lot of people are concerned about intermittent spurious emissions, both in the NOCOM communications area as well as stuff like satellite signals. So of course, we've been doing spurious emissions tests for years and years. Usually that's done with the SWEP-tuned spectrum analyzer. And in general, it's not real difficult to do if the signals are CW. Obviously, the more dynamic range you need, the more challenging the measurement becomes. Then there's also the speed factor. But in general, we've been doing those standard types of spurious emissions measurements for a while. But it goes to a second level. We've got more restrictions now potentially, and we've got some signal intelligence type of applications that want to know all the emissions that they may be transmitting, or on the other hand, they may want to find them, both in the comment and ELINT space as well, as a subset of the SIGINT space. Also, for agile communications, things like cognitive radio might be something that you may be familiar with in the kind of the extension to software-defined radio in the MILCOM space. Of course, frequency hopping has been around in military communications for quite some time. That's another application where it's very agile as far as the signal goes. That's also happening, of course, in many other avenues where your bursted types of signals that are moving around. Even, for example, wireless LAN obviously is agile in some cases where it can actually move in frequency as well, or analyze and transmit in a band of frequencies. Of course, modern radar, we see things like, of course, radar in general, because it's typically a bursted type of signal. We also see, of course, with new actively electronically steered arrays where it's very, very fast transitions and you're really moving around pretty quickly. You also see it in of course, jamming, or essentially EW space, where you're trying to of course, jam those radar signals. And then finally, some people want to just test how things are switching. So maybe an oscillator, a VCO, how it turns on, how it switches, how long does it take to settle, different types of modes that different types of communication devices are in, and then of course down to the, like I mentioned earlier, down to the component or subsystem where maybe it's doing something in a different mode and changing frequency. All good areas where people want to find dynamic or transient events, and maybe today they're having some problems with it. So when do you use a time domain versus a frequency domain approach to find transient signals? So I've kind of grouped this. This is obviously a very high level, maybe a little bit crude way of breaking this down, but the time domain is when something happens. It's very easily understood to see when something obviously happens because you're looking at it in the time domain. So it makes it easy to understand relationships to other events. Obviously, if you have something like a pulse signal, you can calculate PRI and those things pretty easily by that type of domain, looking in that type of domain. Calculating peak power and pulse width, those types of metrics, as well as finding repetition, so you can kind of see how often something happens over and over and over. And then to look at the instrumentation, generally we look at an oscilloscope, which is obviously typically wider bandwidth. They have a really high sample rate. Obviously, Agilent has a 66 gigahertz oscilloscope in analog bandwidth. So it's very, very wide band. It also has advanced triggering that enables you to trigger on different types of signals in different types of ways. Also, it can do, with the triggering, it can do something like a segmented capture where you only want to look at certain times, which is more memory efficient. It is both phase and amplitude, so you get not just a vector representation of, or excuse me, not just a scalar representation of the signal. So you get a good understanding of both how the signal is performing in both amplitude and phase. In the frequency domain, it's really useful to look in the frequency domain when you have somewhat of a crowded spectrum. So if there's multiple signals coming on, especially at different amplitudes, you want to trigger on those types of things, that becomes very, very difficult to do in the time domain. So to decompose a crowded spectrum, to understand what types of signals they look like, sometimes it's easier based on the envelope of the signal that you can kind of get an idea of what it is. Also, frequency relationships. Are the frequencies changing? Are they dynamic? Are they coming in and out? That is another probably a little bit easier way to see how those activities are happening in the frequency domain. And then for instrumentation, again, I talked about signal analysis. Typically, we use a signal analyzer, or what some of you may be familiar with, spectrum analyzer, back in kind of the legacy version of that. Typically, it's higher in frequency, and I mentioned 66 gigahertz, but for the cost, it's typically higher in frequency. You get really good dynamic range. It's obviously can be scalar or vector. The traditional spectrum analysis is all scalar. So the vector analysis is typically pretty narrowband, and we can talk about that as well. So probability of intercept, what are we trying to do? So we're trying to find an event that is of a specified duration or longer. That's basically a number we're trying to reach. So if I said I want to make sure I find any intermittent signal that's 1 microsecond or longer, then you would like to find that 100% of the time. So the percentage of that, obviously, the probability of that that you're going to find those is in a percentage. But there is a next level to this type of analysis. You just want to detect the signal. Are you concerned about fidelity, how accurate it is? Is the power, very important to you? And do you want to catch every single event, or is it okay, like I said, probability of a sub 100%? So those are all factors on what kind of probability of intercept you would like to analyze. So we're going to talk about these four kind of different types of probability intercept as we go along today. So looking here, this is kind of, again, the traditional swept analysis, what you would see with a spectrum analyzer. Basically, it sweeps across. And if your signal lasts for what would be the y-axis here on this green, so if you break this into a triangle and you take this side of the triangle, if your signal lasts for that long, anywhere in this frequency band, then you're going to see a response there. If it happens in some subset, like let's just say it happens here, that information, as you see in the orangish color, is lost. So the advantages are it covers a really wide span. You are sweeping the LO across. It's magnitude only. We talked about that. There's no phase information, and also the data is lost, obviously, as I just said, whenever the LO is not present at the point where the signal's at. So if the signal's not on when the LO is there, you miss the signal. So for what we call at Agilent IQ Analyzer or basic mode, basically this is what we do when we stop and stare. So we park the LO, and we have a given IF bandwidth. We digitize the data, we FFT the data, and we get both the vector data. We get the vector data as well as the scalar data, of course. So again, this is usually done in bursts. So if you can look again at this on the screen here, you can see that. See if I can get a pointer here. So you can see here that you see the green area is where the information is actually being acquired, and then what happens in the orange area is where the information is actually being analyzed. And while it's being analyzed, we are not collecting new data. So it's a batch mode. So you can see down in the bottom left here, you're missing information. As you go along, the time would be the time samples. You're missing some of that. There are gaps there, and you are missing some signals. So your probability of intercept would have to be longer than your processing time. So what is real-time analysis? Again, it's gap-free, usually what we talk about. So real-time meaning we get, in the last example I said, where you do some analysis. This is basically where you sample all the data, and all of that data is processed and it's continuous. You don't miss anything. It has a consistent speed, typically, where all the hardware is implemented in an FFT, so that there's no degradation to things like operating systems that start up and say, okay, hold on, I gotta do this other process. I can't process that data. It's very high speed. We're going to talk about what that gives you in detail later in the presentation, but many thousands of FFTs per second, which vastly exceeds what you can do in software. And by that I mean on your Windows platform or your Mac platform or your Linux platform, whatever you so choose, doing those on a general processor is much more difficult or impossible. High-speed displays, where you combine a large number of these measurements into form a responsive, something that you can actually analyze and produce some sort of insight to what is going on in the signal spectrum. And so that's a very important thing, as I mentioned earlier, because even if you do catch the signal, you have to make sure that you knew that you caught it and you know what it is. So this is the use case here. So you park the LO for a given amount of time, or excuse me, an infinite amount of time potentially, and you acquire data. And while you're doing the acquisition, you're actually doing the processing, as you can kind of see down here from the bottom left. So the data is actually collected in parallel. Generally, for doing real-time spectrum analysis, you lose the vector information. So you strip that vector information, even though you are doing FFTs. But then you need advanced displays to process that large amount of data. This is a simplified block diagram of a real-time system. So you see that there's a digitizer at the top. It digitizes the data. Generally, real-time corrections and decimation are done after that. And then there's one of two paths that you can go in. So you have basically now you have the information is Hilbert transformed. Let's say now we're in the IQ domain. And you have two paths here. I'll do the left side really quickly. So the left side would be a time domain process. We talked about some of the advantages of doing time domain analysis, but basically what you do here is an I squared plus Q squared square root type of thing, where you just take the scalar amount of that analysis, and then you can get something like a power versus time display. So you can do, again, measure pulse width, timing, those types of things that I mentioned earlier. Then on the right side, this is the frequency domain analysis, where you have some overlap memory. And the reason why you want overlap memory is because, let's just say that you have a sample rate that's, for your ADC, that's slower than the amount of time you can do FFTs. Then you need some of the old samples to do a new FFT. So basically you have a use case where you're taking old samples plus the new ones that come in, and then you do an FFT. So you do them at a constant rate here, and quite a few of them. And then this is an important block for many reasons, but to take it at a really high level, you have all those FFTs, and you hold them in memory. And the reason why you hold them in memory, well, there's multiple reasons, but one of the reasons is because this display processor obviously is never real time. So no matter what general operating system you're using, you're not going to be able to see the display necessarily in real time. So this memory makes sure that everything gets held and makes sure that it always posts to the display eventually. So that's a really key point, that makes sure that you get all of the analysis that you see. So there's three different types here. I'm going to talk a little bit more about this in a minute, but yeah, we'll go along and we'll talk a little bit more about this. So what happens in the FFT block? I mentioned the overlap memory, and this is kind of how it works. So you have a bunch of IQ samples that come in. These are represented by these dots here. Then you have a window function. So this is the FFT, one of these, and this could be something like, let's say, for example, a Hanning window, where you apply some sort of multiplier to the actual IQ data, and you come up and you do an FFT, and you come up with something that looks similar to like this. And then you do the next one. And then you use some of the old samples from the previous FFT, and you do another FFT. And obviously in the darker blue here, you can see that there's some overlap between the two windows. And again, that's kind of represented here at the bottom, where you got 50% overlap, where each FFT is using half of the samples for the subsequent FFT. And again, you're doing all of this processing in parallel to the acquisition, so there's no gaps in the data. So to look at what we typically would say in the analysis world, what would specifications look for probability of intercept? Basically, there's different things in signal processing that can potentially give you results that are not equal to what you would see as a CW signal. So for example, here we have a CW signal in, and we have a signal barely sticking out of the noise, and you can maybe see this green level here. I'm maybe have to squint your eyes a little bit, but there is some green above here, not black as typically seen on a signal analyzer. And you want that amplitude reading to read exactly what it would be as if it were a CW signal. So for example, if you have some signal that's on for some subset of the duration, and you turned off the modulation, or you turned off the pulsing, the CW would be equal to what you would see if you did turn that pulse on. So a lot of times you want to be able to trigger on those events, and usually that's done using what we call frequency mass trigger, which I hope to talk a little bit more about that. But basically the idea behind it is that when a signal goes above a level, in this case this green area, that you create a trigger, and you can do some analysis from that trigger. So we'll talk a little bit more about that so it wasn't really clear. Again, we will talk a little bit more about it. So windowing basics here. So we call what could be called off-bin or on-bin, which typically you see some kind of scalloping if it's off-bin. Basically, if you have an even number of wavelengths in the FFT, then you get a really nice response. But if it's off-bin or it's not, there's not an even number of wavelengths in that FFT, then you get stuff like degraded signal-to-noise ratio, inaccurate representation of the signal, and in general just poor visual representation. So here we got a signal. You can see in blue that one's off-bin. The green is, I think, a quarter off-bin, and the red maybe a third or a half off-bin. But basically you can see three different types of signals, some that are off and some that are on-bin. And then one last thing to talk about the FFT, just in the frequency domain, you may know that the larger the FFT, the narrower the resolution bandwidth filter. So if you're familiar with spectrum analysis or signal analysis, you're familiar with what a resolution bandwidth filter is, but basically it will help do two things for you: lower the noise floor. The smaller the resolution bandwidth, the lower the noise floor. It's the noise bandwidth inside of that. And then also the better resolution you get, so you can see two signals that are closer together if you have a smaller resolution bandwidth filter. But again, the larger the FFT, meaning a big number for the FFT for the amount of samples you take and do the FFT with, the narrower the RVW. So there's some variations, of course. Again, you know, for taking something like a rectangular window where it does not attenuate the samples as much, you get sometimes, if it's off-bin, you get very poor representation of the signal. So that's why rectangular windows aren't used quite as frequently. And again, you get a signal-to-noise ratio degradation. So using other windows, you can maybe get a little more forgiveness on the FFT. The way that the signal is represented visually, as well as how it responds in amplitude, depends on the different types of windows. So again, we'll talk a bit more about this, but the more what I'll call attenuation you get as the signal gets further away from the center of the window, and we're going to take a look at that in a minute. So there's different types of windowing. I kind of mentioned some of these, but you know, rectangular window, not real good if it's off-bin. But it is good in some other domains for doing probability intercept. So we're going to talk a lot more about that as we go along. The Blackman, Harris, Hanning, and Kaiser are kind of in between different types of windows. You can obviously get a lot of information about how those windows perform in for different types of signals. But the flat top window, I'll just mention this one, is really good for holding that amplitude accuracy. Doesn't have that scalloping issue quite as bad as you may see from the rectangular window. So you can see that the amplitude variability from these three signals, again, the blue one on-bin and the other two are off-bin at different amounts, very, very close to the same amplitude for those signals. So what about signals? So the general rule, if you're not overly familiar with it, the general rule is that signals that are shorter than an FFT typically, well, not typically, they will not have an accurate amplitude accuracy. So in order to get an amplitude accurate representation of the signal has to last for the entire FFT. And it's important to note that it has to, not just the amount of samples for an entire FFT. So for example, if it started here in the middle and then ended here, maybe it's enough points to be one FFT, but it's not in a single calculation of the FFT. You're going to have degraded amplitude. So for example, if you had a signal that's on for maybe like this signal, some portion of the FFT, then basically what happens is you're going to have a degradation of amplitude based on the ratio of this amount of area under the curve versus the total area of the window. So again, the smaller the signal, the harder it is to get an amplitude accurate measurement. And again, you want to make sure that if you want to get an amplitude accurate signal, that it lasts for the entire length of the window. So let's take a look at some examples here. So we're gonna clock the sample rate at 200 megahertz complex. We're going to do 1024-point FFTs. We're going to want full amplitude accuracy for in this case that would be 512 microseconds. And we're going to take two different examples. One where a quarter of the window is basic. The signal lands in the first quarter of the window, as you can see here in red. And then the other is in blue here, as you can see, where it lasts in the middle of the signal. So assuming that those two use cases, you can see what I was talking about earlier about the attenuation, where the signal actually starts here at the beginning. It's not as obviously it's near zero at the very end, and much smaller here. So you can see that the cumulative amount of signal area under this window is much larger in the blue case than it is in the red case. If you added up all these coefficients versus these ones, you're going to get a much larger number in the blue case rather than the red one. And doing the calculations for this, you can see here that, for example 1, the signal will, meaning the blue case, the signal will be minus 4.125 dB down. And then example number 2, where the red case, where it's barely at the very beginning of the window, you're minus 29.129 dB down. So you can start to see where the signal actually lands has a big effect on what the representation of the signal is. And in the end, we'll talk about how it relates to probability of intercept. So let's see what the effective sample rate is. So basically, the sample rate, in my eyes, way to explain it for me is that the sample rate changes the time scale. So the same number of FFT points, but they really come faster. So if you're doing a 1024-point FFT, let's just say this is obviously not 1024 samples, but the understanding is that you squeeze these together. And so a signal that lasts for a specific amount of time, again, showing it in the bottom, you can see that there's a lot larger amount of area underneath this window than there is over here. It's a smaller amount as a ratio from the total window. So you get a better representation in the bottom case. So a faster sample rate typically will help you in being able to analyze signals and make sure that they're amplitude accurate. So let's look at the effective overlap. So the FFT clock, again, I mentioned this earlier, is running faster than the sample rate. So that means you're doing more FFTs. You're doing FFTs faster than there is samples coming in. So you have to do overlap, as we saw on a slide 5 or 6 slides back. So we have to calculate the number of points, back to our example using a 1024-point window, you take the clock speed of the FFT engine minus the clock speed of your the sample rate clock, and then divide that by the amount of, again, the FFT clock rate, and then you get the number of points. For example, for a 1024-point window, I'm showing a 300 megahertz FFT clock and a 200 megahertz sample clock, and you can get, as you see here, 341 points of overlap. So it's basically a third times 1024 gives you 341, or a little bit bigger, I think, than 341, but we round down, of course. So while I'm on this slide, let me mention one more thing. So I know some of you may be like, what are these numbers here? And I'm going to explain in a little bit more detail what these asterisks are as we go forward. So for full amplitude accuracy, again, the signal actually must stay on to guarantee that it lands in a complete window for almost 2 FFTs. It's actually 2 FFTs minus 1 sample. And again, the reason is because if it lasted for 1024 samples, it could start in the middle of the window and end in the second FFT in the middle of the window. This is an example maybe of one that has 0 overlap, so that would be a higher sample rate in this case than the previous example. But the point is that you have, in order to guarantee that this signal, which could be represented in blue, lasts long enough to fit in one full window, it basically has to last almost 2 FFTs in this use case. So again, if it's 2047, 1024 plus 1023, then you can guarantee that it either start at the first sample here or end at the last sample here and one of these windows would have a full signal in it. Otherwise, if it's some subset, I can arrange the signals to where it does not fill an entire FFT in each case. Okay, so we talked about doing 1024-point FFTs, and we talked about windowing. There's another thing you can do, and obviously you can also window and zero pad for the rest of the signal. So this is this use case. So basically, you could do a 1024-point FFT, but only use a 32-point window. So this is this example. So basically, we got two FFTs, again 1024 points long, but now the window's only 32. So you have to make sure that it lasts for two windows. Earlier I should have said it must last for 2 windows. So basically, you got the first window here, then you go whatever 1024 minus 1024 samples from the beginning of this to the start of the next FFT, and then you have a 32-point window. So if you add the 31, then you're guaranteeing that the signal will fall in at least one of these two 32-point windows. So again, this is a use case with two FFTs doing 1024, but only using a 32-point window and zero padding the rest. And then if the signal lasts for a full amount of the window, then you get an amplitude accurate representation of the intermittent signal. So maybe this is starting to become a little bit more clear, hopefully, but the number of samples in the signal that must last are, again, equal to the CW signal is represented by this equation here. So the window size plus the FFT size minus the number of points, and then minus 1 sample. So then to calculate the duration that the signal would need for full amplitude accuracy, the minimum signal would be that number of samples, as we just calculated, divided by the sample rate. So again, we talked about how fast those samples come, are again in the equation here. So for example, if we had that use case as we showed in the previous slide, this one here, where you have two 32-point windows with obviously 2 FFTs for each of those, you get a use case like this where the window size is 32 points, the FFT size is 1024. So again, this 341 is in here because even though that the windows aren't overlapping, the FFTs are still overlapping by 341 points. So this is the FFT overlap here as the number of points. So you got 341 minus 1 gives you 714 points, and then if you could either multiply that times 1 over the sample rate, or just, obviously we're doing that here, 714 divided by 200 gives you 3.57 microseconds. So example number 2, using a 1024-point window with 341 points, and now we're using a much larger window. Again, like I said, we're using the 1024-point window. Again, 341 points of overlap because it's FFTing, the window is the exact size of the FFT. So you got 1024 plus 1024 minus 341 minus 1 gives you 1706, and then the probability of intercept of that would be 8.53. So hopefully that was clear. That's the basics of calculating it, and now you can see where both the sample rate and the overlap are pretty key in determining what your ability to accurately analyze a intermittent signal is. So we talked about the frequency match trigger. I gave a quick introduction to it. Again, basically the way it works is you can probably see this one's a little bit clearer where there's some greenish color here. There's some black in between the actual noise and the signal, and then you see what the CW signal is. But if your CW signal was at the top of the screen, let's just say here, and you had what 60 dB of the signal into the mask, then you can give away some of that amplitude accuracy and still make sure that you get a trigger 100% of the time. So let's take a look at that. So the goal again is to calculate. The use case could be to calculate what the duration is required if the signal is 40 dB above the mask, again using that 200 megahertz sample rate that we've been using previously. So the worst case is that the signal as at sample 854, which is 683 plus 171, or you could say, I think 1024 minus 171 would, I think that would give you the same number. But basically, one full FFT, and then you back it off a little bit because it's right in the middle between the two FFTs overlapping. That's where the 171 is the 300 and what was it I had on the last slide? is 341, obviously, divided by 2. So that's where, right in the middle between that overlap is where you get the signal. So you can see it's represented in blue here. So the sum of the coefficients must reach 0.001 times the sum of all the coefficients to make sure that it's minus 40 dB down. So again, if you did 20 log of 0.001, you should get minus 40 dB. So for example, if it were 60 dB down, then you would do 0.001 times the sum of all the coefficients. That's what it must equal. So these have to total up to at least 0.001 as a sum. And then we'll show here that in the window example, that means for a rectangular window, so that would be 11 samples, and the Blackman-Harris would be 65 samples. And the reason being is because if you had a rectangular window, it's basically a square, right? So now those coefficients are much, much higher. You're not attenuating them as much as you would in the Blackman-Harris. And now you can see where a rectangular window, though we talked about scalloping and issues with the on-bin versus off-bin, where the rectangular did not perform as well. That is true, but it is useful for things like this to make sure that it's a fewer number of samples you need to get the probability of intercept number that you may desire. So now we're going to lower the sample rate from 200 megahertz to 100 megahertz to see what does the effect of overlap have on the signal. So again, when you lower the sample rate now, then you have to, that overlap memory, you're using more samples in that overlap memory because you have less samples coming in via time, and you're still clocking the FFT at the same rate. So again, the FFT is clocked at the same rate, so you're still doing FFTs at the same amount, but then now you're lowering the sample rate, and it gives you more overlap. So now we're summing the coefficients again to reach the 0.01 times the sum. So for a Blackman-Harris window, for 100 megahertz, that would be 8 samples, and then for 200 megahertz, that's 65 samples. So even though it takes twice as long to take those samples, as we talked about in the example where we squeeze those windows because of the sample rate, it takes more samples to actually get the amplitude accuracy that we want in the signal, or the probability of intercept that we're trying to get. So it goes from 325 samples to, 325 nanoseconds down to 80 nanoseconds. So here's a kind of a use case where when you can trade off some amplitude accuracy of the signal, you actually are better off using a lower sample rate than you would be otherwise. So this kind of illustrates that. So again, on the top here now, I have the duration of the signal, but with a offset. So we're going back to the picture where we had the two. One was CW and it was right at the mask, and the other one was at CW that went way into the mask. So if you made a pulse, or if you had that signal only lasted a specific duration, depending on how deep it went into the mask, or how much amplitude accuracy you can trade off from 0 to 60 dB, you can see the plot here. And then this goes back, I'll explain the asterisks again. So before I had asterisks here, and basically what that meant was that the windows were overlapping. So remember, the FFT is always overlapping in the use case, because even the fastest sample rate is, in our use case, even the fastest sample rate is slower than the clock speed. So the FFT's always got overlap. But depending on what size window you have, depends on how much overlap you have. And in this case, again, we're using a 1024-point Blackman-Harris window, so we always have overlap because it's a 1024. But that's what that was in the previous slide, and I'll show you another example of that here in a sec. But you can see for the larger offsets, you can see that sometimes lowering the sample rate actually will improve your probability of intercept down to 10 nanoseconds, for example. So this is for a rectangular window, which in many cases is a really good way to, if you just have one signal and you're just trying to catch it, the rectangular window is a really good choice to use, specifically with a wider window. And so here you're seeing that it doesn't have as much of an effect for overlap because there's not as much attenuation on the skirts of the window. So you don't see as profound of an effect of overlap in the rectangular case as you would have in potentially like something like a Blackman-Harris window, where it has that tailing skirt to it. But again, you can see that you can trade off the duration, or excuse me, the amount of amplitude accuracy for being able to guarantee you trigger on it 100% of the time. So now I want to take just a couple minutes and I want to talk about repetitive pulses. So this might be pretty straightforward, but you got a subsequent, or excuse me, a sequence of pulses that are coming in from a device maybe into a signal analyzer. And then this could be your 32-point window. So you're doing 32-point windows and then you're zero padding the rest, but you're always doing 1024-point FFTs, zero padding on the other areas. So what that could look like is something like this. So you have a certain amount of overlap, and then you can see here that we have the signal eventually lines up. So basically, the more repetitive the pulse is, the better your probability is of eventually catching it. Now, the big kind of rules here is that the sample rate obviously has to be at a different rate than the signal rate that's coming in. Because if these were happening at the same time, they didn't line up right, you zero pad the rest and you completely miss the signal. So first of all, you can't be synchronized, and the second thing is the string has to be long enough to where, statistically speaking, you're eventually going to have this small duration signal that lines up with your window. So again, here is the density display. I talk a little bit about these different types of window. Basically, the density display is a histogram of windows. Basically, again, we do a lot of FFTs. So again, in our use case, we're talking about nearly 300,000 FFTs in a second. Your human eye cannot understand how those work. So basically, or can't comprehend that at that rate, even if the display did update exactly one every 5 nanoseconds, for example, or less, even if it could update that fast. So essentially what you see here is a bunch of different colors, and it's very difficult to see on this axis, but there's a color bar. And so for each FFT that you have in each one of those, they're all added on top of each other, and for each bin or point on this XY display, so let's just say we have 900 on the x-axis and 300 on the y-axis. For each one of those points, if the FFT happens to have a hit in those points, then you keep adding them up. So doing 300,000 FFTs, let's say you update the display every 30 milliseconds, then you have 10,000 FFTs, so it aggregates 10,000 FFTs. So the noise hits a lot more often, so it gets a brighter color. These didn't have any hits, so it got 0, and this signal's moving around, and it's on the bottom of the scale, so it gets blue. So maybe it had maybe 5 hits or 3 hits over those 10,000. Real-time spectrum is another type of display where you can add markers to it. We can do band power markers and other types of markers onto it, but the point is that this is an aggregate of those 10,000 traces that are added in. So whatever detector you put in, for example, if you use the peak detector, it would be the peak of all those 10,000 FFTs. Spectrogram you may be familiar with. On the x-axis is the frequency domain. Y-axis is the time domain, so this would be going up via time. And then you could see that the amplitude corresponds to what the color is. So it's hard to see probably in your screen, but there's a color bar here, and the higher amplitude represents red, and the lower maybe a bluish color, and you can see how you can represent amplitude. It's kind of a three-dimensional display there. Power versus time is actually in the upper right, but basically that's what zero span would be. The advantage of power versus time, again, it's real time, so you may not know, but a spectrum analyzer is not real time in zero span. You probably do know. So this is a real time mode, as we talked about in the block diagram. And in addition to that, it's also where you do zero span in a spectrum analyzer. You're limited by the resolution bandwidth filter as far as rise times and pulse widths to make sure that filter settles. In this case, it's the digitization bandwidth. So you get a much wider. You can do much narrower pulses in something like the power versus time display here. So frequency match trigger, to talk about what it is really quickly. Basically, again, you can see we have some signals. You can set it up to say, all right, I have some, this is like a 4-carrier wideband CDMA signal. I want to make sure that any signal that's outside of this signal, I want to trigger on. So you set up a mask, you can set up the different points. You can maybe see these little green things here, the little green circles. Those points you can drag around, you can edit them as you want, or you can do it in this table here. And then if there's a spur or something that pops in, it'll trigger. And you can trigger a measurement, you could trigger a recording, which we're going to talk about in a minute. And again, it's a way to be able to, you can export the trigger to a scope to do an acquisition, but it's a good way to be able to trigger on events that happen infrequently. And again, the lower the noise floor and the larger the signal is into the mask, the lower your probability, well, I should say the lower the duration of signal for 100% probability of intercept. So again, if you use some post-processing for deeper analysis, you can see here the advantages is that you can mix and match FFT. So again, I said that you could do a frequency match trigger and trigger an IQ capture. And if you did that, you could reprocess it and get amplitude accuracy by mixing and matching FFT window sizes, mixing and matching the length of the FFT, and different types of overlap. You can actually view it sample by sample, for example. So some really good advantages to using post-processing for deeper type analysis. You can do correlation techniques. Again, you can visualize the data in just about any domain you want. And you can typically get more measurements, like you could do demodulation because you're getting IQ data. So you can do a lot more measurements potentially offline after you acquire the data. So you can trigger on an event, capture it, and then post-process it. Some of the trade-offs in general, if you just record it, is the acquisition is limited. Again, if you use the trigger to record it, then you get some efficiency there, but as I mentioned down here, and it's an easier implementation. But if you just recorded it, it's much more longer analysis time, so it may only occur once in a very infrequent amount of time, maybe once a day or something to that effect. Using a trigger to trigger on it, then recording it, and then post-analyzing it's much more efficient than doing a day's worth of IQ capture. So just to kind of give you an idea, obviously we're doing this for a reason. One of the reasons is because the PXA now has real-time analysis capability, and this is actually upgradable inside of the instrument. We've actually been shipping this hardware that we're taking advantage of for the past 3 or 4 years. So this hardware is already been out there. So if you have one of these wideband PXAs, you can just get a license key and you can turn it on. But that's the product we're talking about, and those are the numbers I've actually pulled for many of the examples above. Then we also have the 89600 VSA software, which is, again, a post-processing tool. I'll talk really quickly about that here in a sec, and then we'll conclude. So here's our specifications. You can see many of these numbers. I said about almost 300,000 FFTs, 292,968.75 FFTs per second. This is both a swept and FFT. It keeps all of your capability of the traditional PXA's, industry-leading dynamic range, etc., as well as 14-bit. And these are the numbers that we talked about. So this is actually for the smallest 32-point window for 100% probability of intercept with full amplitude accuracy. So as you know today, for example, in the pulse case where you have a bunch of different pulses, as long as that pulse ends up eventually lining up with a 32-point window, then you don't have to do that two FFTs minus one sample, business that I talked about before. And you can actually measure pulses consistently at 100% amplitude accurate down to like 160 nanoseconds. So again, if you have some signal that is going to be further into the mask and you have a signal-to-mask ratio of greater than 60 dB, then you can measure signals that are as short as 5 nanoseconds in this use case with our sample rate and our overlap, our FFT processing rate, which also equates to overlap. We also offer, of course, different window lengths, so 32-point to 1024-point windows. Those are, you're probably getting it's powers of 2, so there's 6 powers of 2 from 32 to 1024, which gives you 6 RBW selections per span. So we decimate depending on span, so you get a whole bunch of different resolution bandwidths, but only 6 per selection on span. And then we give the gambit of filter types that I've kind of reviewed already today that can optimize the type of measurement you want to look at. Again, the PXA gives great dynamic range. We have this low noise path option that really gives you really great industry leading, even for a signal analyzer, minus 157 dBm per hertz in the X band for radar and electronic warfare. And we give excellent dynamic range across a full 160 megahertz of bandwidth. This kind of shows the frequency hopping thing, and you can trigger on that, and then you can post-process it, kind of going back to what I mentioned earlier about going, you have something that's moving and you may want to be able to trigger on it and analyze it and do demodulation. Our product is the 89600 software that allows you to do that. And again, as I mentioned, you can go sample by sample and look at it, window it in all kinds of different ways, and really slice it 17 million ways till Sunday to be able to analyze that signal and demodulate it and really get good analysis. And it works in conjunction with the internal analyzer and the frequency match trigger capability. So you can trigger a recording with this and analyze it in the 89600 software, which again gives you all these measurements, a whole bunch of them. I'll let you look through that quickly. And then basically this is what we bring. We bring the best probability of intercept, the best spur-free dynamic range. We talked about the frequency match trigger and that probability of intercept, as well as the ability to analyze really complex signals and dig deeper. And finally, it retains all of the capability that you have with your PXA, with the really high performance, noise figure, phase noise, those types of metrics that you also want to measure on devices. So I ran a little bit late, but I wanted to say thank you again, and please let me have some questions, and we'll hopefully I can clear up anything that you may have. And again, if we don't get to all the questions, we can certainly take those offline and send you emails for responses.
Great, thank you, Ricky. Before we start the Q&A session, I'd like to remind everyone about the survey. Agilent holds many free webcasts throughout the year, and we ask that you take a couple of minutes to complete the feedback form that will appear when you close the WebEx session. This enables us to help deliver the content that you need. Now on to the Q&A. If you have a question, please enter it in the question window. And we have some that have already come in. So Ricky, here's the first one for you. The question is, are you implying that there's an FFT engine in the hardware? Please provide more details.
Yes, I certainly am. So, so again, this is done in signal processing. Let me see if I can find a slide here. So it's inside of, it's not done in post-processing, so we actually have an ASIC and an FPGA. The ASIC does, let's see if I can get back, here we go. So we have FPGA resources inside of the instrument that do the FFT, this block here. And then in this block, we obviously have a proprietary ASIC that does all the real-time corrections and decimation. So all of this is done in what we'll call digital baseband hardware, not in a general-purpose signal analyzer. So we have FPGA that, again, is doing this very, very fast.
Okay, great. Thank you. Next question is, how can I recover the accurate signal amplitude and duration even if the amplitude is degraded because the signal is too short?
Yes, so good question. That is, again, that kind of goes back to the frequency match trigger case. So again, if you trigger on the signal and record it, then you can use different types of windowing and different types of different size windows in a post-processing world. And then since that signal amplitude data is all in the IQ data, you can still analyze that signal. Let's see if I can get to that slide. You can still accurately analyze that signal. Now, obviously, at some point it degrades because of the fact that, if your signals, for example, 500 picoseconds, which is very, very fast, and your sample rate is you're only getting a sample 1 every 5 nanoseconds, you're not going to ever get full amplitude accuracy with that. You just, you fundamentally run into a wall. But again, if you have the ability to do smaller windows and you can, your sample rate's high enough, then on the order of, tens and 20s of nanoseconds, you can start to, in this use case example, you could start to get more accurate amplitude accuracy.
Okay, great, thank you. Next question here is also about the frequency mask trigger. Why is the frequency mask trigger more useful for capturing transients than an oscilloscope?
That's a great question. So the answer to the question is, for example, for an oscilloscope, if you had in a time domain a whole bunch of different things happening, let's say, for example, I don't know if I have a good screenshot, it might be hard, but you can kind of, if you really squint and see, you can kind of see there's a whole bunch of different signals happening here. And basically the oscilloscope's seeing all those signals at the same time. So if you have a big signal and a small signal, and you want to trigger on the smaller signal, in relation to the bigger signal, maybe it's different in frequency, meaning it has a different frequency component to it, but the amplitude is in the same band of interest as other signals. It's much, much easier to be able to use something that you can select via the frequency domain than you could via the via the time domain. So if there's a bunch of different signals in there, it's hard to capture one of them. Again, it's much better to use something like a frequency match trigger to be able to selectively see both amplitude and frequency, and you can pick things out much easier than you would otherwise with an oscilloscope.
Okay, thank you. And our next question is, if you have hopping frequencies, can the PXA follow along?
So yes, the short answer is yes. The longer answer is it can depend. So obviously we talked about, well, maybe we didn't, but I went through kind of fast on that spec slide. We have 160 megahertz of bandwidth, which gives us that sample rate that the 1.25 times 200 gives you 160. That's basically our bandwidth. And so if the frequency hopping is happening within 160 megahertz, then you can certainly see that and I'll say follow along with it, but analyze it. If it's happening outside of that 160 megahertz, then obviously you're not going to see it unless you change frequency, and then once you change between the two frequencies, it's not real time, obviously. So if you move from one to the other and move in a different frequency, then you're not getting more than 160 megahertz worth of real-time bandwidth. The real-time bandwidth is within 160 megahertz. Hope that answered the question.
Okay, yeah, great, thank you. Next question here, how do I upgrade my PXA to get the 160 megahertz analysis bandwidth and RTSA?
Yeah, so basically, again, as I mentioned, if you have the wideband option, that hardware target is where the FPGA and the ASIC basically reside. So that board we've been selling it for quite some time now. Or if you have, it's the same board as 140 megahertz. You may be familiar with that. We first released it at 140 and then expanded it. But if you have that board, then it's you again contact your local sales guy. But you can buy the upgrade option, and it's a license key. You get a certificate. You download the firmware. You put the firmware in, and the firmware changes the hardware, so to speak, by FPGA. Right, it reprograms the FPGA, and then you get real-time analysis.
Okay, great, thank you. And one last question here. Do you have real-time IQ streaming on the PXA and MXA, and can you comment on how many samples you are able to store internally?
Yes, good questions. So we do. We have 40 megahertz of real-time streaming IQ out of an LVDS port from the PXA, for example. And so you can store as much as a RAID array can hold, and we have partners that we work with to be able to do that. So you can buy an external RAID and you can keep streaming terabytes of data at 40 megahertz. The other question is how much can we store internally? So like let's just say you did the FMT and you used your 89600 software and you captured the IQ data. At full rate, we can at 160 megahertz we can store about 2 seconds worth of data. So obviously, if you're at 80 megahertz, for example, you can store twice that amount. So you can do 4 seconds. So there's you can scale it based on the amount of span that you need, or the amount of data that you actually need.
Okay, great. Thank you very much, Ricky. So that's all the time we have for questions today. If there are any that we did not get answered today, we will follow up via email. Before we close, Ricky, any closing comments from you?
No, we'll get back to anybody else who we didn't get questions, and thanks again for attending, and if you have any questions, let us know.
Okay, great. Thank you again for your presentation. And as we wrap up today's presentation, remember we will email you a link when the on-demand version is ready to view, along with a copy of the slides. And if you're currently viewing this on demand and have a question about any of the email or any of the material, you can please email Ricky at richard_overdorf, that's OVERDORF, @agilent.com. I'd also like to remind that I'd like to remind our on-demand viewers to complete the webcast survey that will automatically launch at the end of the webcast. Thank you again for attending today's event, Understanding Probability of Intercept for Intermittent Signals, brought to you by Agilent Technologies. The copyright of this presentation material is owned by Agilent.